So now let's look at the situation when M is linear. It's a vector space, and phi is also linear. So then, after the first step, we have the integral to the determinant Lx delta dx dx. So, just again, Lx is Ea phi x, and so basically now what we want to do is, well, we have the g orbits, and we want to have transversal lines through these orbits, to these orbits. Well, it's clear that there will be some points where it will, or rather there will be some orbits which will fail to be transversive. But we still can, so if this actually, I'm sorry. So we want to choose a linear constraint and say if we have a finite collection of orbits, then what we really care about is that they intersect transversely in the vicinity of these points. Okay. So then in this case, we can simply split the space M into the kernel of phi plus the complement M prime, and the M prime will be
well, you mentioned that the space itself is linear.
The space itself is linear, yes. So otherwise there is no linear function. There are no linear functions. So I guess I have to be a little more careful. So now we have the kernel of phi in M. Then that's an embedding. So we have the map of tangent spaces, and that gives the subspace the image of the dphi in the tangent space of M. I mean, M is a vector space. Right. So the tangent space is a vector space. Right. So at any point we have the subspace in this vector space, which is the image of the kernel. So it's just, I mean, it's just.
In this case, the derivative of phi is phi itself, right?
It's phi itself, yes. So it's.
And so if you take d phi from the kernel of phi, the tangent space to the kernel of phi is the same as the kernel of phi.
Exactly.
And d phi is equal to phi, so it looks like
exactly.
that map is 0.
Oh, okay.
That okay, well then.
So it's actually kernel of phi.
So after I think that's
okay. So then we also have the G action, and so at any point A, which is the kernel phi, so this azimuth kernel phi. So we have the splitting where this space is isomorphic to G. So basically what I want to do is, I want to because it's a linear constraint, so I just want to integrate out those directions where this is non-trivial. So I want to integrate out the sort of the g directions, the ones along which this function is constant and this one is constant. So wait. So I want to write this as the integral over. So now let's say I want to write this. So I'm talking about the integral over the epsilon neighborhood of the critical point A of function f. So this is S A f of S H and then so locally we have the line of the constraint SP, that's the kernel of phi, and then we have g directions. So I want to write explicitly the integral as the integral over the surface of the constraint. So this will be so this is let's say that EA acts on functions as a first order differential operator so then this will be equal to sum over I L I A X phi I A. So here these are the,
and I guess the LIAs are not independent of X.
no, they do depend on X.
Oh, I'm sorry, it's the action.
This-
Yes, no,
this
phi's
is-
are linear, but
that's-
action is still not linear.
That's the whole thing.
Yeah,
Right?
yeah,
We still
absolutely.
have the
I'm sorry.
vector fields.
Yeah, exactly.
So then it will be just the determinant of L. Now it depends only on S, on the transversive directions ds. So So now what we have to do is we have to write the formula for the asymptotical expansion in H of these integrals. I mean, the delta function disappears, so these Lagrange multipliers disappear together with the delta function. And this matrix still describes the action of our Lie algebra on the surface of the constraint, and now this is simply the integral over this small neighborhood plus C A L A B S C B D S D C bar D C, And then this also can be the asymptotical expansion of this integral. It's again given by the sum of Feynman diagrams, where we will have only the propagators corresponding to the derivatives of S. So we will have the fermionic propagators and only one kind of bosonic propagators corresponding to the expansion of this function in coordinates S, near critical points. So I don't know if I should do it in details. Probably I should. It's so, and this is the formula that will be relevant. So that's the formula that, for example, was used in Chern-Simons by Kontsevich, by Axelrod and Sinker, in order to derive the Feynman diagram expansion. So the integral in question is asymptotically equivalent to H, same powers, I'll denote this GA signature GA, and GA is the matrix of second derivatives of F restricted to the surface of the constraint. So 1 plus sum, and then the same thing, fermionic Feynman diagrams. It's difficult to talk about this subject and not to use the physics terminology. So, so this is d of gamma. So here dij A is the second derivative with respect to coordinates on the surface of the constraint of F restricted to S of A. This matrix is non-degenerate because we first restrict to S and then we take the critical points on the surface of the constraint. The rest is the same, except now the diagrams will have weights of edges given by dA inverse ij, and they will have the same fermionic propagators. So this will be minus ILA inverse AB, and then the weights will be simply the nth derivatives of the function f with respect to the coordinates on the surface of the constraint. F S of A, and the same thing as we had before, where the fermionic vertices meet the edges meet the bosonic edges. So the expansion of the, so this will be I d L d as I1 d as IL of L AB restricted to the surface of the constraint at the point A. This is A and this is B. So these are the Feynman diagrams in case when our manifold is linear and we choose a linear constraint which is still transversive to the critical orbits. So this cross section, this constraint, this surface as phi, the kernel of phi, it can be positioned rather badly to many orbits, but all we want is the transversality to the critical orbits. The rest is not important for this asymptotical expansion.
And we could even localize the integral to the critical orbits first, and then choose individual slices.
Yes,
to
exactly.
all of them.
So that's right. So there's this great flexibility, and it's exactly because what these expressions are is these are the coefficients of the asymptotical expansion. So these are super local things. So in some sense, all we need in order to write this formula is not some kind of global information about the geometry of M or on the sort of structure of the function f on the global manifold. It's a super local information. So it's just the formal neighborhood of every critical point or every critical orbit. Okay, so this is these are Feynman diagrams for in case when there is an action of G. So now let me emphasize the structure of the degeneracies here. So let's look at the function f on some smooth manifold n. So what kind of critical points this function may have? So it may have simple critical points, which means that in every direction it's a quadratic function. So it may have something like this. There are two directions. In one of the directions it's a quadratic function, in the other direction, so it's like x squared, in the other direction is x cubed. This critical point is already degenerate. The Hessian at this point will be 0. These kind of degeneracies can happen varieties of ways. So the Hessian will be 0, critical points will be degenerate, but sort of these are not the type of degeneracies we're discussing here, or the type of degeneracies of that usually are considered in quantum field theory. So in gauge theory. So for us, it's the following. The function is non-degenerate in certain directions, and it's constant, strictly constant, in other directions. So, for example, in the case when we have G acting on M, we don't require that F is quasi-invariant, in the sense that the action of, infinitesimal action of G moves it very slow away from its value at some point. We require that it's strictly invariant. It means that it has F is constant on orbits, and we also require that it's non-degenerate in the transversive direction. So it means that it's non-degenerate, all critical points are non-degenerate on M cross G, on M mod G. A more general situation of this kind is when we have a distribution, when we have at every tangent subspace, we have tangent space, we have a subspace, and somehow this subspaces very smoothly sort of pasted together. In this case, we may still require that the function is constant in these directions with respect to this distribution. Not for every distribution such functions will exist, they will exist for integrable distributions. So this would be the generalization of this situation. And I don't think so the most general case will be, say, something like a function which is constant on a non-integrable distribution. But such functions don't exist. So, but this is more or less the subject of so-called Batalin-Volkovitsky quantization. So the next, so this is what we discussed is Fadeev-Popov. So this is the case of Young-Mills, Chern-Simons. But then there are these more general cases when the function is not constant along the orbits of the G group, but along the along some distribution. And so this is when the technique known as Batalin-Volkovitsky quantization is used. And somewhere in between there is an algebraic version and there is some kind of algebraic observation that is related to Fadeev-Popov quantization. And there is one example where this technique is really essential, where you cannot get by Fadeev-Popov, or where you cannot get by a variation of it, sort of known as BRST. So it's the nonlinear Poisson, so it's a so-called Poisson sigma model. That was the fact discovered by Kansevich that formal deformation quantizations of Poisson manifolds can be described by two-dimensional quantum field theory considered in terms of finite directives. Formal deformation quantization, it's the formal power series which defines associative operation on the Poisson algebra. So here you can see formal power series, and then there is a very special quantum field theory that's called Poisson sigma model, which produces formal power series which describe the deformation quantization of Poisson manifolds. And this formal power series quantization does require this more general approach. So you can, when you read the literature, you will see many papers on Batalin-Volkovitsky and various aspects. It's a very nice algebraic structure which was independently discovered in earlier than Batalin-Volkovitsky. was discovered by Gerstenhager in deformations of associative algebras. So it's a certain algebraic structure that is in some sense more general than BRST algebraic structure, which can be used in many ways. So just for purely algebraical purposes, or it still can be used for these purposes. So I think there are many interesting developments already in this field, and there will be more probably there, because the complete understanding of this Poisson sigma model, which is behind Kancevich's quantization, is still lacking. It's maybe I'll say at the end a few words about this. So the main problem there is, as it is now, it works fine for disks when space-times are disks, and when you glue them together, you glue two disks together, and then it's homeomorphic to a disk again. So it's a variation on the space-time categories. But say if you will put some surface here, and we'll start to glue surfaces, it would make sense because the theory exists for disks. but for surfaces the theory is not developed yet. So, okay, so this is just some deviation, and the goal of this deviation was to emphasize the kind of degenerate functions that we are interested in. We are not, at least yet, interested in this kind of degenerations, which is, for many reasons, most important kind of generalizations, but not in this context yet. So, now I want to say a few words about the RST. So let's look again at this Faddeev-Popov function. So it's f of x plus this minus this. And it's a function on the supermanifold So what does it mean that it's a function on this supermanifold? Well, it means that Ft belongs to the tensor product C infinity on M cross G, tensor the exterior power of exterior algebra of G plus G star. So here coordinates are x and lambda, and here generators are C and C bar. So now let's look at the yes, Volodya yesterday was complaining that I explained what the Grassmann algebra is, I explained what the integration is, but I didn't explain what the differentiation is. And now I regret it, he was right. So I should have said what differentiation on the Grassmann algebra is. So let me briefly recall what it is for those who know and introduce it for those who didn't see it. So Grassmann algebra is the algebra generated by elements CA with the defining relations is 0, or it's naturally isomorphic to the exterior algebra of CA, where CA is a basis in CA. So the left derivative of the monomial CB1 CBN is simply the following. If we have CA standing on the left, it is simply annihilated by this derivative. If we have CA standing on the second place, first we have to move this derivative through the first entry of the monomial, and that gives -1, and so on. So this is equal to delta A. So let's assume that B1 Bn. So this is delta A B1 CB2 CBN minus CB1 delta A B2 CB3 CBN plus, and so on. And then in order to annihilate CA if it stands on the last place. If it stays on the last place, we have to move it through n minus 1 C's. So this will be.
You don't need that B1. This sequence is monitored. Why?
Just for convenience, because this is this is the action on the base. It's not necessary.
But the formula is still true if you.
The formula is still true for any b's, of course. Yes. Okay. So now I want to introduce the.
Maybe you should just mention that the integral of the property, that integral of the derivative is 0.
Yes.
In order to.
That's one of the properties justifying the word integral is that if you take the definition of the Grassmann integral from the last lecture, then it has the property that integral of the derivative is 0. That's a formal analogy with the.
And the Leibniz rule is always satisfied.
And the Leibniz rule, yeah, that's true. But so the Leibniz rule is the super Leibniz rule. So now it's df dCA g plus minus 1 to the parity of f. And the assumption here is that f has a certain parity. Parity means parity is 0 if it's a polynomial in C only with even degree monomials. If it's a polynomial degree with only odd degree monomials, then the parity is 1. And this f bar is the parity of f, and the assumption is that it has a parity. It's not the sum of even and odd terms. It's either even or odd. F dg dc. Okay, so now the VRST operator, it's the sum over A from 1 to n, sum over I from 1 to d, C A, and then this is essentially the action of the Lie algebra on functions. So I'll write it slightly differently. So these are the structural constants of the Lie algebra. Plus sum over A, lambda A, d dc A bar.
F-A-B-C.
Yeah.
Yeah.
Yes. So now, so this is obviously the action of the generator A of the Lie algebra G on the manifold. Yeah, so it's a Lie algebra homomorphism from G to vector fields on M. Simply written in local coordinates. So now let's just look at this differential operator and see what's remarkable about it. Well, there are two remarkable facts about this operator. First, and this is a great homework exercise. So I'll not waste our time here, but it's really it's a very simple thing, but so to check it once in a while in your life, that's a good exercise. So the idea of Popov function is a cocycle for this differential. But before I will say that the word cocycle, I should say first that it's a differential. Q squared is 0. So it's a differential from algebraical point of view. Physicists call such operators supersymmetry operators. So in physical terms, this is certain supersymmetry which exists on the space of X, lambda, and ghosts. So, and the second remarkable property is that the Faddeev-Popov function is conditioned as follows: as f of x plus q ERST of something that you may also find in the literature by the name gauge Fermi. Okay, so here there is some kind of disaster. I switched from C to C bars. So I think in the previous notations C bar had an upper index. So it's a homework exercise to kind of fix the notations. Okay, so this expression, and sometimes it's called gauge Fermi. And as soon as we will start to use this terminology, it's a step towards the Battalion-Volkovisky quantization. So this is part of the terminology of the BV area. But you can see from here that, well, apparently what we have is on this space we have the structure of the cochain complex with the differential QBRST. The Faddeev-Popov function is a cochain, and we know its cohomology class. Its cohomology class is the original function f that we started with. So we have an interesting setting. And if you look at this construction for some time, you will start to recognize the well-known algebraical features. So first, when we have the, let's look at the situation when we have the functions on M, tensor the exterior powers of G star. So this is naturally the direct sum over N, and then maps, linear maps from NG to C infinity N. So this is a well-known construction. It's a Chevalier complex for the Lie algebra G with coefficients in C infinity. With the differential given by in these notations, it will be the first term, CA. So we identify this exterior algebra with the Grassmann algebra. It will be CA EA minus 1/2 sum over ABC F ABC CD CC D DCA. That's the first part. And the second part is it will take C infinity functions on G, tensor the exterior algebra on G. So this is we can identify this with the forms on G. So when we have a manifold G, so I want to make sure that I'm not confused between G and G star. And I may, so let's see. So I just want to check the polarity here. So it's so the tangent space to G is G again, and form.
It looks right.
It looks right. So
Actually wrong. Sorry.
let me write the Ram differential first, and then we'll see whether it's right or wrong. So the differential is it's just sum over A lambda A d dc bar A. And
But I mean, let's not. I think it's more important to.
I think it's more important just to have the structure. I mean, somewhere I made a mistake. Somewhere it's G star instead of G and G instead of G star. So, but you know, if you have a vector space V, so what's the Ram differential on this vector space? So what are the forms on this vector space? Well, anyway, so it's a homework exercise.
But shouldn't it be the causal complex on the constraint lambda? So this lambda define a subspace M inside of
Lambdas, no. There are no constraints here anymore. It's
it looks perfectly like a causal complex on the equations lambda is 0.
on the equations.
Lambda
Lambda
is just
just coordinates.
Now, our coordinates, so we can define coordinates to be 0. So lambda 1,
Yeah,
2,
that looks good.
Yeah.
Yeah.
So, but it looks like Kazul maybe, but it is the Ram. So, I mean, you see, maybe I should go through this. If it's confusing.
But we sort of almost over time now for you. So.
Oh, okay. So then
Sorry.
let's start with this. We will start with this next time, and we will have a little more discussion of PRST. And after this, we'll pass to quantum mechanics. And also, so everybody is welcome to complete the homework exercise about the part that was the beginning of the first lecture. And I'll